I'm going to do some physics right now. I'm going to start with number 17, chapter 2, and keep going until I get to number 29, doing the odds. Let's see what we got here. These are constant acceleration problems. And this is the way I'm going to do them. With a constant acceleration problem, after I read the problem and determine that it is in fact that type of problem, I'm going to make my little list of the quantities that show up in this type of problem, and then I'm going to determine which one of these equations I need to use, and then I'm going to write that equation down, and then I'm going to go from there. That will be my MO. My mode of operation. If you speak English, if you speak Latin, you might have another way of saying that. Let's see what we got here. An electron has a constant acceleration of positive 3.2 meters per second squared. At a certain instant, its velocity is 9.6 meters per second. What's its velocity 2.5 seconds earlier and 2.5 seconds later? Okay, so I guess we just need to figure out what, this is two problems. So for part A, it's 2.5 seconds earlier. So for that situation, its acceleration is 3.2 meters per second squared, and its velocity. Now here, since this is the, they're asking what's its velocity 2.5 seconds earlier, that means the 9.6 meters per second will be its final velocity. And looking for the initial velocity. Let me say that again, just make sure that makes sense to you. If we're talking about what's the velocity 2.5 seconds earlier, then this is the final velocity, and we're interested in finding this. Now, this might be just very obvious to you what the answers should be to this, because when we have constant acceleration, the rate of acceleration is just the linear change in the velocity. So if you want to dial this back 2.5 seconds, this is how much it's changing every second. So you just need to multiply that by 2.5 times the rate of acceleration, and then subtract it from this, and then add it to this. Of course, that's exactly what our equation does. So that's fine too. So we can set up the equations if we want to. It's going to be VF is equal to AT plus VI for both parts. And that here, my VF is 9.6 is equal to 3.2 times 2.5 plus VI. And here, 9.6, oops, just kidding, VF is equal to 3.2 times 2.5 plus 9.6. So you can see how we're going to get the two different versions of the answer. You can check in the back of the book and push the buttons on the calculator there. All right. 29. I'll tell you what, physics, people who teach physics and do physics, intro level stuff, like what we're doing, we love elevators. We really do. A certain elevator cab has a total run of 190 meters and a maximum speed of 305 meters per minute, and it accelerates from rest and then back to rest at 1.22 meters per second squared. How far does the cab move while accelerating to full speed from rest? How long does it take to make the non-stop 190 meter run starting and ending at rest? Okay, so it's going to... We got 190 meters total, and it's at the beginning. Let's say it's going up. So for a little portion, let's say here to here, this is what it'll be accelerating here, and then it's going to reach its cruising speed and cruise, and then it's going to decelerate or have a negative acceleration. If we call that the positive direction, its acceleration would be the other way, slowing it down. All right, so I guess we need to figure out, well, we need to do a little conversion here first. I need to know, this is the its constant speed while it's there. They say that it's 305 meters per minute. I think I would like to have it in meters per second. So that's about 5.08. And when it's doing this, it has an acceleration of 1.22 meters per second squared. Its initial velocity would be 0 because it's going to start from rest. Its final velocity will be this, the cruising speed. It's got to get up to speed. Oops, I was going to write a square there, but this is just a velocity. There we go. And we need to know what this distance is right here. Do we want to know distance or time? What are they asking us? How far does it move? I think we need both. So I'm going to need this. Now I'm going to do something crazy here. I'm going to call this, instead of delta x, I'm going to call this delta y. Why do you think I'm doing that? Well, this is moving up and down. So to me, I mean, this feels more like a y-axis, and I mean, this is just the name of a variable. So you could call it delta x. You're going to get the same thing, right? But it seems more like it matches onto my experience of what x and y mean if I call this y. So that's also foreshadowing time in the not too distant future where we're going to need x's and y's, and that will be that kind of decision will be more important obviously then. All right, so we need to find these two things, both of these. You can ignore that announcement there. Oh, code yellow drill. I'm missing all my students. I miss you guys a lot. All right. Sorry about that interruption. So first, let's find this delta y. That looks like the equation VF squared is equal to VI squared plus 2A delta y. So my VF, 5.08 squared equals 0 squared plus 2A times delta y. And that delta y is going to be a little bit of calculator magic. Oops. Is going to be 10.6 meters, we'll call that. I think I entered that all properly. It looks good. Okay, so this is 10.6 meters. And I don't know if you feel like you have to do the math again up here. Because of the symmetry of this and the way our equations work, I'm very easily convinced myself that the deceleration, if it slows down with the same acceleration here of negative 1.22 meters per second squared, that's going to take exactly the same amount of time and cover the same distance as when it was speeding up from 0 to this, then going from this back to 0. If this is the rate of change of the acceleration, then to get from 0 to this, changing by this much every second, if you go from this back to 0, changing by that much in the negative direction, it's going to be the same. So I'm not going to redo the math for that. Now, I do need to set up my other equation, or maybe you just realize that, hey, if I'm going from 0 to this, and that's my linear rate of change, it's going to come down to just dividing my velocity by the acceleration, because I'm going to have to add 1.22 every second until I get to this. Of course, you can write the equation down if you want. It's going to be the same one we used in number 27. 5.08 divided by 1.22, and you can see how it turns into that. All right, that it turns into that division problem. So let's see what we have. Have we answered any of the question yet? How far does the cab move while accelerating to full speed from rest? So I think for part A, the answer is 10.6 meters. That's what we got there. And for part B, how long does it take to make the nonstop run? Okay, so we have a little bit of work left to do. I think that I know that the time here, that's how long it's going to take for this part and for this part of the run. But I have the whole constant velocity part in the middle. So, well, what's the distance while it's going its constant velocity? This 190 meters, that's the whole thing. So what about this distance? Well, it's 190 minus those. So 190 minus a couple of 10.6s. So this is about 169 meters. I'm keeping 3 sig figs for all my answers. And then going this distance at this constant velocity. So back to my constant velocity, let's see, if you have a constant velocity, then that's just your distance divided by time. Right, I put a delta y there because I'm going up and down. So my constant velocity, 5.08, is equal to 169 divided by that time. A little bit of baby algebra, and I'm going to get about 33.2 seconds. So my time total is that time that we're just cruising plus my 4.16 for getting up to speed plus 4.16 for slowing down. So that's about 41.5 seconds. And I'm just going to flip to the back of the book, and should have bookmarked this ahead of time, but I'm going to find here my answers real quick and make sure that I am telling you the truth about that. So let's see, I did already have it bookmarked, and this is number 29, so this is 29, 10.6, 41.5 seconds. Yep, great. And I even have the same significant figures as the book. How about that? All right, so 31. Suppose a rocket ship in deep space moves with a constant acceleration equal to 9.8 meters per second squared. It starts from rest. How long will it take to acquire a speed 1/10 of the speed of light, which travels at 3 times 10 to the 8th meters per second? Okay, so in part A, I've got a rocket ship with an acceleration of 9.8 meters per second squared, and it's going to start from rest, and we're going to get up to 1/10 the speed of light would just be 3 times 10 to the 7th instead of the 8th. That's fast. That is what we would call relativistic speeds. That's where weird stuff starts to happen because of general relativity. And special, well, just relativity, I suppose. So how far will it travel and do? Sorry, this is for part A. How long will it take? And part B is how far will it travel? So I'll just put that there too. So for part A, how long will it take? That looks like I have my VF equals A T plus VI. Of course, this is the same situation from rest. If you're ticking up this much every second, You just have to divide this by your rate of acceleration. If you plug the numbers in here, you will see that that is in fact exactly what is going to happen. So 3 times 10 to the 7th divided by 9.8, so we about 3 times 10 to the 6th. So we'll say 3.1 times 10 to the 6th, we're dividing by 10 about meters. Sorry, this is a time. That's seconds. So I don't know, what's that? 3.1 million seconds? You could, if you're interested, do a quick conversion of this. That's probably something that would be better measured in some larger unit of time, like hours or days or years or months or whatever it is. So just for fun, let's do that real quick. So if you have 3.1 times 10 to the 6 seconds, if you divide that by 60, you're going to get minutes. If you divide by 60 again, you're going to get hours. And if you divide by 24, you're going to get days. So let's check in there. So I think that's where probably a reasonable unit would be, about 36 days. All right. There's my time. Now to find the delta y for part B, now if I'm not interested in that, that's going to be my VF squared equals VI squared plus 2A delta y. Did I say delta y here? I don't know, I guess I'd probably call this a delta x. Because the rocket ship is going up. Either way, doesn't matter what's in a name. A variable displacement by any other name would smell as sweet. That's weird. Displacements probably don't really smell like anything. So 3 times 10 to the 7th. Math. So I have 3 times 10 to the 7th squared divided by a couple of 9.8s. Get 4.6 times 10 to the 13th. That will be in meters. So we're doing all SI units here. And again, you know, that might be helpful to see, like, how far is that, you know, on in some other kind of unit. It's really, I mean, in kilometers, it'd just be 4.6 times 10 to the 10th kilometers. Which is what, 46 trillion? No, 46 billion meters, kilometers. Again, maybe not so helpful. Is it more or less than a light year? Well, if you're only going a tenth of the speed of light and you're only doing it for about 36 days, then it's definitely much less than a light year. I think that it's about 3.6 light days, right? You can think about that. Let's just check the back of the book here, make sure that all those answers are good. For number 31 in Chapter 2. Yep. Bingo. Yahtzee. All right, so 33. Can I just point out to you, I know I'm a professional physics teacher and everything, but I want you to see, if you just stop for a second, take a deep breath, close your eyes. Okay, open your eyes again. Now I want you to look at your work. Look at your physics work, like how you're setting up these problems, how neat they are, and how possible it would be for another human to look at your work and make some sense of it. So I'm trying. I'm not like the neatest person in the entire world, but I want you to look at like how much stuff I have going on here. Now I know that I'm doing these problems in a very teachy kind of way, but I don't think I'm doing a lot of extra stuff, and I don't know. If you look at your work and it just looks like a big pile of garbage, compared to this, you might consider trying to just be a little bit more neat. It really helps. It helps the neatness of your thinking to have neatness of presentation. And the further you get in any kind of real problem-solving endeavor, the more of an issue this can be. Because, you know, real problems, like actual problems that people need to solve, like really, not problems from a textbook, it's not going to take like some little part of one page. It involves an enormous amount of organization of material. All right, sorry, get off my soapbox now. 33. A car traveling 56 kilometers per hour is 24 meters from a barrier when the driver slams on the brakes. Going to jot down some of these details. When the driver slams on the brake, 24 meters, okay. I'm not really sure if that's my delta x or not, so I'm going to leave that blank for, I'll explain why in a second. From a barrier, the driver slams on the brakes, car hits the barrier, so 2 seconds later. So that my time is 2 seconds. What's the magnitude of the car's constant acceleration before impact, and how fast is the car traveling at impact? So I think that this is my delta x. So those are the three things that I know. I know that it was going this fast, it went that far, and it hits. I don't know what the final velocity is. I think that's part of what we want to find, right? Yeah. So we want to find the two missing things. Acceleration and how fast is it going when it hits. Okay, so just need to figure out which equations to use for part A. That looks like my delta x is equal to 1/2 at squared plus vit. Okay, time to do math. Are you expecting to get a positive or a negative acceleration here? Let me ask you that. What do you think? And once you start doing the math, I think that you can see what the answer to that is pretty quickly. All right. Let me just check that before I go any further. Make sure that that's right for you. Number 33. No. What am I doing wrong here? I have a bad feeling about that. Let's see. I think I messed up some mathematics here somewhere. Oh. I'm mixing my units here. I didn't convert that to meters per second. It's a careless blunder. Let's see, 56 kilometers per 1 hour. I need to change kilometers to meters. And then I need to change hours to seconds. So, in short, I need to multiply by 1,000 and divide by 3,600. So that's about 15.6. So let's see, that's where that showed up. And get rid of that answer and make a new, better one. So let's see, I got to back up here a little bit and fix my math. Be right back to you. Then that's better. All right, I think that jives with the back of the book. And then part B, I would like to find this final velocity here. So let's see what we have here. I think that's going to be my delta x is equal to 1/2 vi plus vf times t. So 24 is equal to 1/2. My vi is 50. Nope, it's not. Just kidding. It's not 56. It's 15.6. Almost did it again. The VF is what I'm looking for, and the time is 2 seconds. So it looks like that 1/2 and the 2 will cancel, so my VF is just going to be about 8.4 meters per second. Quick check. Make sure it's true. Hope you do the same thing here. Yep, that's good. All right. There's a big page full of physics right there. How are we doing? 26 minutes. That's not too bad. And we have, what was that? That was 33. So I have 35. And we still have, wait. Hold on. Why did I write this? Sorry, I wrote this at the beginning. That was freaking me out for a second there. 27 to 39 is what we're doing. So I have 3 more, 35, 37, 39. 35. Uh-oh, they've got 2 dots now. We're in trouble. Just kidding. I wish they wouldn't put those dots next to the problems. Just intimidating unnecessarily. So we got a graph here, figure 224. It's a little picture above. Red car and a green car. Looks like they're aimed toward each other, and that move toward each other. And it's graph. Oh, and then we got a graph in figure 225 also. That looks kind of like. There's one that's curving. So if this is position time, if we've got this curving, if this is a parabolic shape, that means we have constant acceleration, and this is constant velocity. So this is the red, I think. Oh no, that's awkward. The red line represents the green car. Who made this? Made that decision. So that's a green car. This is the red car. That makes sense with right being the positive direction if we look at the picture of the cars. Okay, so some details here. Their positions. So the initial position of the green car that has this constant negative velocity is 270, and of the red car it's negative 35. Okay. At time t0. The green car has a constant speed. A constant speed. You got to be careful there. Speed means they're not telling us. Speed doesn't care about sign. Now, according to this graph, that constant speed of the green car is definitely negative, right? The constant velocity, rather, is negative if we care about the sign, and I think we do. And the red car begins from rest. What is the acceleration magnitude of the red car? And they meet each other at 12 seconds. All right. So there's a couple ways you could approach this. I'll tell you what seems to appeal to my sensibilities is I think I would like to figure out where this is, and then I can set up the little acceleration problem for the red car. Now, if this car in 12 seconds, the green car is going at this constant velocity. So in 12 seconds, the green car is just going to go 12 seconds times 20 meters per second. It's going to go 240 meters in the negative direction. So this is going to be at 30 meters right here where they cross each other. Now, if that seemed like a little bit like, whoa, slow down, McGrath. Got to apply some negative acceleration there to your thought process. You're way ahead of me. You can always set up the equation here that constant velocity of the green car is equal to the displacement over time, right? For constant velocity, that's all we need. So that's a G there, by the way, not an S. So that's negative 20 is equal to, it goes, now this car's also going in the backwards direction, so we'd expect this displacement to be negative, and it's happening in 12 seconds. So there's your math, delta x, negative 240, so you end up at 30. So now for the red car, we're going forward 65 meters. So my delta x is positive 65 meters. I don't know what its acceleration is. I'm looking for that. I'd like to know. It went from rest. Yes, red car begins at rest. I don't know what its final velocity is, but I know that it happens in 12 seconds. So there we go. I got three things. That's what I'm trying to find. That looks like my delta x is equal to 1/2 at squared plus VIT equation. And let's see what we got here. Delta x, 65, 1/2, looking for A, times 12 squared. Initial velocity is 0, so that's gone to 0. And so what do I have? I've got my acceleration is 65 divided by half of a 12 squared. So, oh, that's just a shade over 1, isn't it? Isn't it 65 over 64? No, just kidding, that's not true. 65 over 72. So my calculator's telling me that that's about 0.90. I believe that is correct. All right, number 37. Figure 2.2-26 depicts the motion of, now where is that figure? Oh, it's right here, this graph. Moving along an x-axis with a constant acceleration. The figure's vertical scaling is set by x equals x sub s equals 6. They like to do this in our book. It's a little bit annoying, but it's the way that they roll. So if that right here is 6, that means it's scaled by 2's, which means that here this is at -2. And then at 1 second, it's right there. And at 2 seconds, it's there. And we get a nice parabolic graph there. They want to know what's the magnitude and direction of the particle's acceleration. All right, well, let's see what we can figure out here. We can figure out, I don't know, if you look at this here and you're wondering, like, does this start from rest? I don't know if we know that for sure. It looks like it might have a horizontal tangent line there, which would mean that, but I don't think we can assume that that is the case. So let's see what we can set up. Looking for acceleration, initial velocity. I don't really know if that's 0 or not. Final velocity, uh-oh, I don't know about that either. So then time and displacement. So unless you want to make that assumption here, which I think does turn out to be true, I think the way I would do this would be to set up a little system of equations, because I do know 3 different locations. So what's going on? So here, what if I look at this first second that's gone by here, from time 0 to time 1? Well, I don't know any of those things, but then I know that 1 second has gone by, and I know that the displacement is 2 meters. Right, went from here to here. And I also know here that in 2 seconds, it goes 8 meters. So if I forget about my final velocities, can I set up the equations that have these things in them? And then I'll have two equations with two unknowns, and I know how to solve that. I did a lot of that in Algebra 2. So let's see if I can do that. So using my delta x is equal to 1/2 at squared plus VIT. That is what we're going to use. And hopefully we're going to find out if we were right about this being a horizontal tangent line here, that should come out to be 0. So for the first situation here, I have delta x is 2 is equal to 1/2, don't know what a is, time is 1 squared plus VI times 1. And then for this one, I've got 8 equals 1/2 a t squared plus VI t. So let me just rewrite those equations, simplifying things as much as I can. I don't really want there to be a fraction here, so I think I'm going to multiply this equation through by 2. 4 is equal to a plus 2 VI. Multiplied that whole thing through by 2. This one, I think I'm going to be okay. Actually, I could divide this one by 2. Let's just leave it like this first. So 8 is equal to, that's 4, half of that is 2, plus 2 VI. And then there is no other problem in all of mathematics that you have ever learned that you know more ways to solve. This is a linear system of two equations, two variables. You have substitution, elimination, you have matrix equations, or the Cramer's rule. That's another kind of matrix way of doing it. And you could, of course, you could solve for something. You could graph them. There's 5 different ways of solving that I can think of right off the bat. I think the easiest way to do this one would be to add the two equations together, but make one of these negative. This is all set up for what is called Gaussian elimination. So if I multiply this equation by -1, stack them up, add them together, boom, that's what we're looking for. So my acceleration is 4 meters per second squared. And does the VI, let's see if that's 4, yeah, VI did come out to be 0, so that was a horizontal tangent there. But I don't know, I didn't feel like I was quite 100% confident enough just assuming that from the graph. So be careful with that. Our book likes, by the way, to set up system of equations problems. All right, last one. Cars A and B move in the same direction in adjacent lanes. And we've got another graph that is the position of car B. Is that right? Sorry, I lost my place. Position of car A is given in this graph. So it looks like car A is going at a constant velocity. And they're scaling this. If you look at where the XS is, that's at 32, and there's 1, 2, 3, 4, 5, 6, 7, 8. So it's scaled by, each one of these little blocks is 4, and this one is 5 blocks up. So that is 20 meters. You do a small amount of work to get that. And if you look at where it's at 6 seconds, it is at the 32 mark. So we might take just a quick second to see what the slope of this is. It went up 12 meters in 6 seconds, so the constant velocity here is, which I'll just call Vx, or maybe call VA. This is car A, right? 2 meters per second is the constant velocity there. Okay. And what else? At time 0, car B is at position 0. If we wanted to put it on the same graph, starts there, with a velocity of 12 meters per second and a negative constant acceleration. So its velocity, that would be its slope, would be like 12, so it's kind of, would be like this, but it's got a constant acceleration, so it's going to bend down. I don't know what the constant acceleration is, but I know that the initial velocity of car B is 12 meters per second. What must that acceleration be such that the cars are momentarily side by side at time 4? All right, so time 4, we want them to be at the same place, side by side. Okay, so, where's car A going to be after at time 4? Sorry, that's probably too close to that. Time 4. Let's see, if it's going 2 meters per second, then in 4 seconds it'll go 8 meters, so that would be 28. That's where that's going to happen. So I need this to just be right there at 28. Now that starts at position 0, so that means its delta x is 28 meters. And it takes 4 seconds. And I want to know what's the acceleration. Okay, so delta x, 1/2 at squared plus vit is the equation we need. And you remember how to find these equations, right? I have lots of practice, so I'm good at spotting which one. But we look at this, we're like, okay, there's no VF, it's missing VF, so I use this one. 28 is equal to 1/2 times, I don't know what, times 4 squared, it's an A, plus 12 times 4. All right, so it looks like my constant acceleration after doing a small amount of math is going to be, let's see, negative 20 divided by 8, negative 2.5 meters per second squared. I think that's the answer for part A. Part B, for that value of acceleration, how many times are the cars side by side? There's different ways of figuring that out. What are the possible answers for that? I think there's really only 2 possible answers. If you think about the shape of this and this graph, the cars can be side by side either 1 or 2 times. If this comes up here and crosses this line and then comes back again, because it is a parabola, then they'll be side by side 2 times. Once when B is passing A, and then as B slows down, because it has this negative acceleration, then A will pass it again. Or it is possible that this is actually the tangent line to that, and that they're only side by side just at that instant, and then A pulls away. So I guess one of the ways to figure this out would just be to figure out, well, how fast is car B going at 4 seconds? Which is pretty easy to do using this. The velocity of that one at 4 seconds, I'm going to put a 4 there so I can really keep track of what I'm doing. I have the acceleration now. It's going to happen for 4 seconds, and its initial velocity was 12. Well, that's negative 10, so sure enough, the velocity of that one at time 4 is exactly 2 meters per second, which is the speed of this. So it is, in fact, the tangent line of that. So they're going the same speed, and then it's going to slow down from there. So that's it. The other way to do this would be to write the equation, the position equation for the constant velocity and the position equation for this one, and see how many times they intersect each other. I'm going to do that for you real quick and show you what that looks like. Oh, after I answer the other parts. I guess I did part C already. I've got the graph here. How many times will the cars be side by side if the magnitude of AB is more or less? So if the acceleration, if the magnitude, that means it would be like -3 or something, then if it was -3, for example, it would be slowing down even more. That would bend it down more, so they would never be side by side. And if the magnitude was less, in other words, if it was like -2, then it would be bending downward a little bit less, and it would cross 2 times. So those are the answers for D and E. All right, so what are the position equations for the two cars? What's the position equation, or position function if you want, for car A? Well, it would be, for constant velocity, position is equal to the constant velocity, which is 2, times time plus initial position. Right? That's like a y equals mx plus b. There's the line right here. There's the intercept, there's the slope, that's it. And then how about for car B? Well, for car B, the position function is that version of this where we just move, this is like final minus initial, I just add the initial position over here. Right, remember that? So that looks like this. And notice that if you have no acceleration, in other words, if your acceleration is 0, then this term goes away because acceleration is 0, and you get VIT plus XI, right? Which is exactly what the equation is for constant velocity. All right, so here I have 1/2 AT squared. Half of that is 1.25 times t squared, plus initial velocity of this thing was 12, plus its initial position is 0 here. Okay, so I could, if I wanted to, put these into my calculator. So I've got, the first one is 2. Calculator's going to make that an x, so that's okay. And then the second one is negative 1.25 t squared plus 12 t. Before I hit graph, I'm going to think about what my window should look like. The times that we're interested in, it looks like we're going from time, I could do 0 to 6, I think that'll work fine. You could go look a little further than that if you want to. And my positions, I could stick with the scaling of this graph and go from 0 to 32, would be probably fine. And then we'll see what that looks like. There is my constant velocity, and there is my constant acceleration. Cool. Did you know that, just in case you wanted to kind of see that happening in real time with the two next to each other, did you know that in your mode that you can go to down here, sequential, what this is referring to is how it graphs your y1, y2, y3. Sequential means graph y1 first, and then graph y2, and then so on and so on. If you go to this simul, that's short for simultaneous, and turn that on instead and go back to the graph, it'll do them at the same time. And in this context, where there's like a physical meaning to these graphs, where they're position versus time, that's kind of cool to see them happening together like that, I think. All right, I'm done.